Okay, so we're gonna pick up from where we last left off in string theory. Last time we discussed about the double action on strings. So I was essentially introducing the physics to you guys, and then we posited that everything we know we have discussed thus far in rigid dynamics and other modes of physics has been a result of fundamental field strings that propagate through space-time. So today I want to teach you guys about, or rather we will discuss about electromagnetism or currents running through the worldsheets of these strings. So before I get to that, I just want to rephrase some of the notation I used last lecture. And so instead of x, capital X of tau sigma denoting a string, we will use capital N. And then our Greek index, our Greek space-time index is going to be denoted by gamma. So I just want to point that out before I list any more stuff. Okay. And what else? So when I was writing this, the induced metric on the world sheet, this GAV is eta mu so Vx mu by Vya and Dx by dyb. This eta originally is meant to be a Minkowskian metric. So the induced metric is affected by the ambient spacetime around the string, or from which the string travels in. So it's really best if you guys replace this eta mu and g mu, because we know that this denotes the spacetime metric, right? So there's that. So if I rewrite my nanobolt action in terms of the string theory, and for a string or fundamental string and gamma, the nanobolt action will be S and G. So this nanobolt action on the string M is essentially d sigma d tau is the square root of my M dot times M prime squared minus my M dot squared and my M prime squared. Wherein my M dot is meant to be what the previous notation was. So dm gamma by d tau, and my M prime is supposed to be del M gamma by del sigma. And the square, I already defined it last time, it is simply the contraction of our vector with respect to the ambient space-time spectrum. Right? So a small note on notation. So instead of using the term x, we're going to use the capital M. I think if I release lecture notes, you guys will see a script M. This is MacCal M, and I use it sometimes, but in my lecture I will make it clear that I'm using the regular script M. Okay. So before I get into electromagnetism, let's talk about flat and non-flat MILFs. So you guys don't know what flat is and not flat. So flat is a seagull. So they're flat as a board, almost like a man. And of course, you guys are the big women. So we're gonna reframe that discussion in terms of our theory. Okay. So what we know is that these fundamental strings generate a world sheet that trace a world sheet through space-time. Now, you could think that locally or globally speaking, those metrics are Minkowskian. So most notably, if we consider an open MILF string, and I trace it through space-time, it looks flat globally, so it's Minkowskian. So the intrinsic metric tensor on this world sheet is Minkowskian by nature. So likewise, the same applies for open strings that travel, or open closed strings that travel on straight paths or straight world sheets. So this is essentially Minkowskian metric in cylindrical coordinates, right? So it's the Minkowskian metric converted to cylindrical coordinates along a certain fixed radius. So I want to make the following definition. So instead of saying that a certain MILF is flat because of their breasts or not flat because of their breasts, we're going to consider the intrinsic metric tensor, which I said was G mu a while ago, or eta mu, into consideration. We're going to take that into consideration. So my definition is as follows. Let M be a MILF with intrinsic metric tensor. So the metric tensor on the surface of the world sheet. So intrinsic metric tensor G mu. So 1, M is said to be flat when G mu is Minkowskian or flat. So what I mean to say is that the metric tensor on a global look of our world sheet is flat essentially. So it may look curved, but locally it's flat. Okay? And the next 2, M is said to be non-flat. So when G mu is not, so M is not Minkowskian. So if I consider a MILF string tracing out the world sheet and it looks squiggly, let's say there's some separation on it. Then we know that this metric, the shape here, this metric is different. We know that it's different locally speaking or topologically speaking. It's not the same as the usual Euclidean or Minkowskian metric. So we can say that this MILF, or the MILF characterized by this world sheet, is not flat. Now, if we consider a simple constant world sheet string, then we can say that indeed this is Minkowskian, albeit with a change of coordinates. R is simply the limit of my sigma. Precisely the radius of the circle generated by the circle traced out by my parameter sigma. Okay? So you can say that now. So instead of simply observing a MILF and then saying, oh, they're flat, or they're thick, they're big, instead, we construct an explicit intrinsic metric tensor on the worldsheet. So we consider the string, the fundamental constraint that generates that MILF, and then we consider the worldsheet traced out by that string. And if the intrinsic metric tensor on that worldsheet is flat or Minkowskian, then we say that the MILF is flat. Not flat otherwise. Okay. So it's a pretty simple definition, but it is it's pretty profound because what we're saying is that if my MILF string has a non-flat Minkowskian metric, even if I'm not looking at the MILF it generates or its worldsheet generates, I already know whether they're flat or not. So while having a surface understanding would allow someone to say with certainty that a certain MILF is flat or not by looking at them, using this physics, we can essentially, using this definition, we can essentially look at only the mathematics of a certain MILF, and we can already tell with absolute certainty if they are flat or not. So that's one of the fundamental definitions that I want to lay out here in our theory. So let's move on, and let's talk about currents on worldsheets. So currents. So I know I didn't discuss much about this in rigid dynamics, but I did encounter gravity. So let's recall the current density field as a 4 vector J alpha, which is equal to the J alpha is equal to C rho times J, wherein J is my component field, which is essentially my current density, and rho over here is my charge density, and C is of course the speed of light. So we know that if this current is conserved, then it must satisfy some equation, right? So we know that if we do some change in so if we measure the derivative with respect to any direction alpha, right, then we know, or any direction x alpha, we know that this guy must equal 0 if it's conserved. So therefore it will satisfy del alpha of J alpha is equal to 0. I'm just doing a review of capital gravity, okay, if you guys have forgotten about currents. So if I separate the indices, I get the following equation. So derivative with respect to the 0 component of my J plus del I J is equal to del J by dx plus the Laplacian over my current. So this over here is simply my time component. This over here is my time component. And this over here is essentially my spatial component. So I take the derivatives of my Ji with respect to each dimension, or each direction. And that essentially gives me the dot product between J and the If it's conserved, it follows this equation. And if we expand it, we get this equation over here. So, now that I know this, I know that my total charge, Q, so when I do Q to be my total charge, it is simply the integral over the volume element. So where the flux happens. So if I have some volume V, this is my volume V, and then we look at the current runs through here. So this is my J. There's some flux going on, and the total charge is essentially the integral. I'm just going to write it out. Okay, so we're integrating over the volume element. So this volume element is our boundary, and then of the charge density with respect to the spatial indices. Okay. And so that would equal then to be integral over the volume element of my zeroth component of my field divided by the smooth light times the x over the spatial indices once more. Okay, so the time derivative of this then would then be the following. So C is a constant, so I can pull it up, essentially eliminate the equation. So if I take a time derivative of my Q, I'll be equal to the same thing, integral over V, except we're taking this the partial derivative of my J0. Okay, so with respect to the zero component. However, we are still integrating over all of the spatial indices. So if I let S denote the boundary, so the surface of my volume element V, then by the divergence theorem, we get that the time derivative of my charge, total charge, is equal to negative times the integral over the boundary of my spatial J with respect to a new direction A. However, we don't take V to be so large such that this over here vanishes on the surface S, and because it vanishes when we take V to be a large quantity, so a very big volume, enough for S to essentially be nothing and J to have no effect, the right hand side vanishes to 0, leaving me with dq by dt is 0. So just like how my current is conserved, we know that the total charge is also conserved. So it's sort of a confirmation. So now what does this have to do with Millstone? So I want to assign a certain form momentum E. So the first step in discussing the currents on your worldsheets. So actually I got to this first. So the general equation for an action of a string. So recall last lecture that the action of a certain object that tell us the position of our spring, or essentially on the surface of our spring, or that dictates or tells us a point on the world sheet, or the world line. In this case, the world line. So we have two DTs, or two indices to integrate with respect to, because we have two directions on the world sheet. Okay, so because we're integrating over, so in general, the action S on my world sheet is essentially d by, so it's a product. So okay, so let's suppose M is a k-dimensional MILF string. So what I mean by k-dimensional is that it can be parameterized, or there are k parameters that dictates the directions or how many dimensions are on the surface of its world sheet. Okay. So essentially we would have, instead of only tau and u, we would have a set of parameters up to k. So I will call them, so with local parameters, psi of alpha, let's call it j. For j, to be 0, 1, up to k. So this MILF string would live in a k plus 1 dimensional space-time. So lives in a k plus 1 dimensional space-time. So, okay, so now I have these indices, and the action on M is the integral over the product from j equals 0 to k. So d psi j. So it's the Lagrangian of my dx dm mu by d psi 0. So d m gamma, sorry, gamma. By d psi 1 to the top up to delta m gamma to delta psi n. So this is the general form, so the most general we can get in expressing the action of a certain MILF string M with k dimensions. Now, because we're only considering a two-dimensional case, because that's the best we can comprehend and we can do physics with, right? So we take k to be 2, right? Or we take k to be 1, essentially. So it reduces to S is equal to d sigma d tau, so Lagrangian over delta m gamma. And for the Namamoto action, this L is essentially my square root of negative g, where g is the determinant of my induced metric G. Okay. So why did I do this notation? Guess we'll see in just a moment. So if I want to find the conserved currents, so I want to find my J over my MILF string world sheet, then we need some variation. And before we do that, we first assign a momentum. So it doesn't matter what specifically it is. We just know that there is a certain momentum over the string. We'll call P mu. That is also conserved. And my MILF string M is moving freely, so no forces acting on it. Okay? So the Lagrangian is supposed to Lagrangian density, by the way. Okay, so now to find my conserved currents on M, so to find conserved currents on my wheel string M, I need a field variation. We need a field variation, which I will call delta of M gamma. So, such that my Lagrangian density doesn't change. So one example of this variation or field variation would be that the delta of M gamma is equal to epsilon mu. And what this means is that for every point on our world sheet, we do a translational movement along the vector epsilon mu. So if I draw my world sheet over here, let's say it splits off just for fun. Then, if this is a point over here, it gets shifted to a new point. So if I have a P1, it shifted to a new P2 along the vector epsilon mu. Okay? And that happens for every point over here. So what we're doing is a spatial translation of our world sheet, essentially. So let's say that epsilon mu is the fourth vector, okay, 0. We're not going to move along the time direction, we're going to move along the spatial direction. Let's say 1, 0, 0, 0. That means if I assign a coordinate system that works like that, so x, y, z, I'm essentially moving it along the x direction, right? So x direction by 1 unit. I'm moving my every single point, so that means the world sheet by 1 unit. Okay. So that is if I assign. If you don't assign a coordinate system or a frame of reference to measure the movement, then it's worthless. Okay. So you guys didn't know this from capital gravity, so I'm not going to talk about it. So now that I have this field variation, so if I multiply the field variation by my J alpha mu, so if I multiply my epsilon mu with my current alpha mu, so this is contracted now, contracted with, if I'm not mistaken, the intrinsic metric tensor of the world sheet. That would then give us the derivative of the Lagrangian density twice with respect to my M gamma. So the M gamma is then equal to derivative of the Lagrangian density times the same expression. So except multiplied by epsilon mu. So I'll leave it to you guys as an exercise to work out that this equation holds, or this relation holds, or happens. So if I cancel out my epsilon, I am left with this expression over here. Okay, so sorry about that. If I cancel out my simply stating my spatial indices, except it's contracted. And then that's equal to essentially derivative of the Lagrangian density by respect to my m dot mu Lagrangian density with respect to m prime. So if you're not clear on what this means, there's essentially just nothing different. So this is a direction, not the direction. So it's the same thing as a while ago, but instead we consider all components of that. Because of course we're integrating the Lagrangian density, that means we're also going to, rather differentiating with respect to the components of this Lagrangian density, which is essentially this m dot, this m prime. So that's for the charge pairs. So for any MILF string M with the Lagrangian density of this quantity, then any charge current or conserved current on it would satisfy this relation over here. And likewise, if I take its derivative, so just like a while ago, I'm just going to bring back what I said a while ago, taking the zero derivative, of my contracted charge or my current, it would still be equal to 0. So it not only satisfies this equation over here, but it also satisfies this equation. So that must hold for any current that runs through my MILF string. So if this is my MILF string worldsheet, then the current would be run through here, right? It would still be conserved. It's a conserved current, and contracted form would look something like this. Okay. That's pretty much it for this lecture. There's not much. I really just want to talk about currents and electromagnetism. I skipped a bunch of stuff just so we can read through this like this. I'm sorry about the noise of the aircon. It's So I based this one, so this part of the lecture was based off of Bartle's feedback. So Bartle's feedback's first course in string theory. So I thought that would be a great place to start off or to discuss our advances from the beginning. Okay. So before we leave or before we end this lecture, okay, so I asked you guys to proving this part here. So another exercise that I'm going to do, guys, is, and it's actually a pretty simple one. It's very fun. So it's a small fun little exercise that you go inside. It's not really required, but I want you guys to find a charge current. Find the charge current and then see where the math takes you, essentially. So play around with these concepts as much as you want, and see where the physics takes you. And you can take it to some really interesting places. So I'm very stoked about string theory because we're now on the leading edge of internet science. So while other internet curators are busy only giving the surface level details on the meaning of some terms, we're going in depth into the actual physics or mathematics of certain things. We are quantifying internet phenomena in order to study them rigorously and quantitatively, essentially. So everything is accounted for almost, I think so. So that's why I'm very excited about string theory, because although it's not a readily proven physical theory in real life, it can prove to be a very nice bedrock. So it can be the unified field theory or unified physical theory that ties everything that we have discussed thus far together. Okay, and it takes just a little bit more effort to show that it does break down to